universally, but also that which is found in every other region, inhabited or uninhabited. But Archimedes is not convinced by this infinite number of grains of sand and sets about calculating how many could actually fit inside the universe. This is his famous sand reckoner, and it begins with a poppy seed. Laying seeds out side by side, Archimedes notes that 40 of them would make up a single Greek dactyl, a finger width equivalent to around 19 millimeters in modern units. And within each seed, he imagines a myriad grains of sand. A myriad is 10,000, the largest unit available to Archimedes at the time. To compute how many grains of sand there were in the universe, he had to invent a new system of numbers, and he also had to estimate the size of the universe. To Archimedes, the universe reached as far as a blanket of fixed stars that formed an enormous sphere centered around the sun. With a series of clever and crude approximations, he estimated the diameter of this sphere to be equivalent to 100 trillion Greek stadia, or about 2 light-years to us. Bringing everything together, he triumphantly concluded that the universe would not be able to accommodate an infinite number of grains of sand. The number would not exceed 10 to the power of 63. How much would such a universe weigh? Well, Archimedes wasn't really worried about that. But if we imagine that each grain of sand weighs around 10 milligrams, then Archimedes' sand-filled universe would weigh about 10 billion trillion kilograms. Oddly, that is not wildly incorrect. But it was just a fluke. Archimedes massively underestimated the size of the universe, and the reality is, it's not all sand. The universe is big. When we ask how much it weighs, we are really asking how much energy it contains. Energy that is stored in the mass of the stars and planets and clouds of interstellar gas. Energy that is stored in radiation, or even in empty space. To figure out how much energy that is, we need to be clear what we mean by universe. We mean an observable universe. That is a large region of the universe as far as the eye can see, or indeed anything else can see. The universe was born about 13.8 billion years ago. This might seem like a long time, but it has not been enough time for us to receive signals from the most distant corners of the cosmos. They are simply too far away. Even if they emit a light signal traveling at the maximum speed possible, that signal would still not have reached us in the lifetime of the universe. This boundary between what we can and cannot see is known as the observable universe. You might think that it must be about 13.8 billion light-years in size, since that is the distance travelled by light in the lifetime of the universe. However, this doesn't take into account the expansion of space. When this is considered, it turns out we could have received signals from objects that are up to 46.5 billion light-years away. And so that is the size of the observable universe. About 93 billion light-years in diameter. Of course, the universe doesn't actually stop at this point. There isn't a giant cosmic wall at 46.5 billion light-years. But we have no way of knowing what it's really like beyond this point. It could be that the universe goes on forever, stretching all the way to infinity. Or perhaps it eventually comes back on itself, like a magnificent cosmic sphere, reaching far beyond the observable realm. This giant sphere would bend the shape of space a little. Light travelling vast distances towards us could be sensitive to that bendiness, and we could hope to detect it. But so far, we've detected nothing. If the universe really is shaped like a sphere, it would have to be undetectably large, with a diameter of at least 23 trillion light-years. But whatever the size and shape of the universe, there is no way we could try and weigh the unobservable realms because we have no way of knowing what they contain. They could be filled with grains of sand, or they could be empty, void of any stars and planets. The rules of physics might even be different there. We just don't know, and we can never know. So if we really want to be serious about weighing the universe, we need to stick to the observable part. Stretching 26.5 billion light-years in every direction. And weigh that. Let's start with the stars. The Sun is fairly typical, with a mass of order 2 million trillion kilograms. Observations suggest that there are between 100 and 400 billion stars in our galaxy, which combine to weigh up to a billion trillion kilograms. There are at least 200 billion galaxies in the observable universe, each containing an average of 100 billion stars. That suggests that there are at least 20 billion trillion stars altogether, weighing a grand total of around 20,000 trillion kilograms. And that's actually not a bad estimate for the stuff we can actually see. But the problem is, it neglects the mass of other sources, stuff like interstellar gas. A better way to measure the mass or energy of the universe is to study its effect on the shape of space-time. One way to do this is to study the cosmic microwave background radiation, the so-called CMB. These are primordial photons left over from the moment the first atoms were formed. These photons have traveled large distances across the entire universe, from every different direction and throughout most of cosmic history. They could even be detected amongst the static in the old days of analog TV. Using state-of-the-art satellite telescopes, astronomers measure the temperature of the cosmic microwave background radiation in different parts of the sky. By measuring the statistical correlations in the temperature fluctuations in the CMB, and understanding how matter, radiation, and other forms of energy affect the shape of space and time, astronomers are able to figure out what the universe is made of. And the cosmic microwave background, in combination with other methods and probes, reveals that the observable universe has around 150,000 trillion kilograms of mass stored in the stuff we can see. Stars, planets, clouds of interstellar gas, and even the human race. That's about 7.5 times our previous estimate. It sounds like a lot, but the stuff we can see is only 5% of the energy out there. There are 2 more ingredients, and they dominate the universe. First, there is dark matter. This is just like ordinary matter that makes up atoms or humans or stars or planets, except it's completely invisible. If you shine a torch on it, the light will just pass through. If you try to whack it with a baseball bat, it would be as if you were just swinging the bat in empty space. We have no way of touching or feeling dark matter except through gravity. It carries mass and energy just like ordinary matter, and so we can feel its effect on space-time. But although dark matter is 5 times more abundant than visible matter, it's still not the dominant ingredient in our universe. That is dark energy. Dark energy makes up a whopping 70% of the universe. Another invisible substance, it is responsible for pushing the universe apart, causing the cosmic expansion to quicken over time. We see this through the light from distant supernova. These explosions are reasonably well understood, and yet the more distant ones are dimmer than expected. This dimming is easily accounted for by the accelerated expansion of space, by the push of dark energy. So just what is dark energy? All the data points towards an exotic substance whose energy density is more or less constant right across the universe. And as we will come to understand, this is just what you'd expect from the energy of empty space. Empty space, it turns out, is not empty. It is really a bubbling broth of virtual particles that can never be tamed, that are forever popping in and out of existence, weighing the universe down, giving it energy, giving it weight. This energy of empty space goes by many names. In the early days of quantum mechanics, most people called it the Nullpunktsenergie, which is German for zero-point energy. Nowadays, people often call it the vacuum energy, or sometimes the cosmological constant. They all mean the same thing, and they are what most scientists associate with dark energy. Our observable universe contains dark energy equivalent to around 46 trillion tons of TNT. And when you put everything together, the planets, the stars, the dark matter, the dark energy, you find a universe containing energy equivalent to 67 trillion tons of TNT. And that is how much the universe weighs. This might seem like a lot, but remember, all this energy is spread evenly across a large universe. The density is very low. The energy is so dilute that a coffee cup full of it doesn't contain enough energy to crush a fairy fly, the smallest insect in the world. And that's just as well, as this low density is what allowed the universe to grow large and old. But in weighing the universe, we now run into one of the greatest of all the cosmological puzzles: the cosmological constant problem. If you really want to think about dark energy as the energy of empty space, then why is there so little of it? But when we take our most tried and trusted theories of physics at face value, we find that the null energy should be absolutely enormous. Our universe should not be the gently evolving cosmos we see today. It should have been born as super heavyweight, instantly crushed under the weight of its vacuum, bent into oblivion in time and space, torn to shreds by the tides of gravity, gone within the blink of an eye. Our universe should never have grown large and old. It should never have allowed intelligent life to evolve. It should never have allowed you to exist.
Well,
but our universe did grow large and old. It did allow you to exist. Indeed, the truth is, the universe is not a heavyweight. It's not even a flyweight. So the question is, why is there so little dark energy? Where is all the Nullpunktsenergie? Why hasn't it destroyed the universe? To understand the Nullpunktsenergie and the puzzle it creates, we have to travel back 100 years to the German city of Hamburg, to a cafe overlooking the banks of the Inner Alster. Hamburg is a vibrant city, risen from the ashes of World War I, a bustling metropolis and a centre of intellectual thought. And in the cafe are two physicists, two friends. Otto Stern is a bon vivant. He enjoys the finer things in life: good food, good wine, good company. He sometimes takes a flight to Vienna just to have lunch. Wolfgang Pauli, however, is a very different character. He is currently sporting a black eye, sustained the night before in the bars of the Reeperbahn, in Hamburg's notorious St. Pauli district. Pauli had been brawling, as he often did, fueled by alcohol and a fiery personality. Stern takes a sip of his brandy and turns to his old friend. "I'm telling you, Wolfgang, the Nullpunktsenergie is real. I've calculated its effects on the vapor pressure of the isotopes of neon. If it were absent, as you say it should be, the difference in the vapor pressure of neon-20 and neon-22 would be enormous." But Pauli isn't convinced. He begins scribbling down a calculation on a napkin. When he's done, he looks up triumphantly. "But what of gravity, Otto? If the Nullpunktsenergie were real, as you say it should be, the universe would not even reach the moon." The Nullpunktsenergie is the energy of empty space, the energy of the vacuum. Consider the universe around you. It is filled with stars that shine their light throughout the cosmos, from the menace of red giants to the sickly glow of white dwarfs. There are hostile planets in orbit around these stars, giant and minnow, too hot and too cold. There are the warm and welcoming planets like the Earth, jewels in the solar system where life can prosper. There are towering clouds of gas, monuments of coloured nebulae, where stars are being born. And all of this stuff carries mass. It carries energy. But suppose a cosmic bailiff were to enter the universe and take it all away. They take away every star, every planet, every human, and all other forms of complex life. They take away the nebulae, the black holes, the bacteria and dust. They take everything, alive and dead, large and small. what would be left? A dark and silent place of true desolation, the most empty of empty space. Naively, you might expect this emptiness to be weightless, to be free of all energy, having been robbed of its wares by the cosmic bailiff. But that is not true. At least, we don't think it's true. Quantum theory has taught us that empty space does carry energy. It carries the Nullpunktsenergie, the zero-point energy, the vacuum energy, cosmological, constant. The celebrated German physicist and father of quantum mechanics, Max Planck, had toyed with the idea of the Nullpunktsenergie as early as 1911, and soon after, it was another German, Walter Nernst, who suggested that the vacuum of empty space was not empty, but an exotic medium filled with an enormous amount of energy. But perhaps the most celebrated German physicist of the time, Albert Einstein, had a turbulent relationship with the Nullpunktsenergie, and also, separately, the idea of a cosmological constant. At first, he was a champion of both. Indeed, it was he who came up with the idea of a cosmological constant in 1917, requiring a repulsive force present throughout all of space to counter the effect of gravity in what he believed at the time was a static universe. He'd also separately teamed up with Otto Stern and computed the effects of the Nullpunktsenergie on hydrogen molecules, their results matching experimental data. But he did not connect the two, and within a decade Einstein had switched camps on both the cosmological constant and the Nullpunktsenergie, supposedly calling the constant his biggest blunder and stating that no theoretician can utter the words zero-point energy without breaking into a half-embarrassed, half-ironic smile. But it would turn out that Einstein was right in his invoking of a cosmological constant, and wrong in his dismissal of the Nullpunktsenergie, and the idea of zero-point energy really took hold in the mid-1920s. For this was when the legendary German physicist Werner Heisenberg entered the game. Struck down by severe hay fever in the summer of 1925, Heisenberg had fled to the island of Helgoland, where he checked into a guest house overlooking the dunes. His allergies were so bad that the lady who ran the guest house assumed he'd been in a fight. Heisenberg used his escape to think deeply about the spectral lines of the hydrogen atom, thoughts that often led to insomnia. And indeed, it was in the early hours of one particular night that a breakthrough finally came, and Heisenberg finally began to understand how the hydrogen atom behaved. He was beginning to understand the sorcerer's world of quantum mechanics, where everything was a game of chance. And as Heisenberg realized, it was a game that led to the zero-point energy, the Nullpunktsenergie. To understand how the zero-point energy emerges, go to the kitchen and take out a large mixing bowl. Throw a marble into the bowl and wait for it to settle down. Eventually it'll seem as if it's at rest at the bottom of the bowl. But is that really true? Can you really say exactly where it is and how fast it is moving? If you zoom into the micro-world, the answer is clearly no. There are air particles constantly colliding with the marble, knocking it to and fro. Okay, but what if you suck out all the air in the room and cool it down to absolute zero? What then? Does the marble finally come to rest at the bottom of the bowl? Or does it wiggle? It wiggles. Heisenberg realized that there was always some uncertainty. The key thing to remember is that quantum mechanics is a game of chance. You can only deal with probabilities. It turns out that the more you know about a particle's position, the less you know about its momentum. So if we know where a particle is, we cannot say how fast it is moving, and vice versa. This means that if we scale the marble down to the size of a fundamental particle, we can never say if it is exactly at rest at the bottom of the bowl, because that would mean we had exact knowledge of both its position and its momentum. Heisenberg's understanding of uncertainty and the laws of quantum mechanics mean that it's simply not possible to know both exactly. In the microscopic world, something always has to wiggle. And so now we can return to our cosmic bailiff, determined to empty the universe of all its stars, planets, and little green men. Before he arrives, the universe is littered with particles, electrons and photons, quarks and gluons, gauge bosons and Higgs bosons, and perhaps even some particles we still don't know about. These particles are, in actual fact, just ripples in the fundamental fields of nature. The photon is a ripple in the electromagnetic field, the electron a ripple in the electron field, the Higgs boson a ripple in the Higgs field. You can imagine these fields as an ocean swell, and the particles as the ripples on top. What the bailiff is really trying to do is get rid of all the ripples, all the excitations of these fundamental fields. He is trying to silence the ocean of reality, to make it perfectly flat. But, as we know, he can't. Heisenberg's uncertainty principle means he can never silence the ocean completely. There's always that quantum wiggle. Tiny, short-lived ripples in the fundamental fields. But these remaining ripples don't correspond to real particles, like electrons or photons you can touch and perhaps even hang on to. If they were real, if you could hang on to them, the bailiff would just grab them and take them away. Instead, they are something more mysterious. They are virtual particles. These virtual particles are forever popping in and out of existence, like a bubbling broth in the vacuum of empty space. They're not the kind of particles you can hang on to, but they do give the vacuum its energy. They give it the Nullpunktsenergie. But is this energy actually real? Or was it just a figment of Heisenberg's imagination? There is a fascinating macroscopic example that helps to answer this question. The gecko. It scampers freely across walls and ceilings. Its seemingly magical ability to defy gravity is thought to have its roots in the Nullpunktsenergie. It turns out that the energy stored in a vacuum through the bubbling broth of virtual particles depends crucially on the shape of its surroundings. Change the shape and you can change the energy. That means that the vacuum will push and pull on the walls that surround it as it tries to lower its energy. This push and pull of the vacuum is a force known as the Casimir force, named after the Dutch physicist Hendrik Casimir. When the walls of the vacuum fall apart, this Casimir force is tiny. But when they're close together, this force is big enough to measure. Changes in the zero-point energy also lead to van der Waals forces between atoms and molecules. And this is what some biologists think is responsible for the gecko's ability to walk on walls. Microscopic projections on the soles of their feet surround small pockets of vacuum, and by altering the shape, the gecko creates a force strong enough to defy gravity. And so now that we've accepted that the vacuum energy is real, we can estimate how big we think it should be. How much energy would you expect to find in a coffee cup of empty space? To figure this out, we need to break space up into lots of little pieces, like a spectacular cosmic jigsaw. The size of the pieces is going to affect our estimate, so we should think about what size we should use. You might think the pieces should be as small as the eye can see. That would make them little boxes about 1 millimeter across. But why would we allow ourselves to be held back by the limitations of the human eye? When Pauli was doing his calculation in the cafe in Hamburg, he imagined jigsaw pieces with sides about 1 trillion times smaller, around a femtometer. This corresponds to the classical electron radius, which was at the limit of experimental physics of the time. And this is where Heisenberg comes in with his uncertainty. If you can resolve the universe into jigsaw pieces just a femtometer across, you can have extremely precise knowledge about where and when a virtual particle pops in and out of existence. Heisenberg says that must come at a price. You must lose knowledge of the momentum of the particle. This means you must also lose knowledge of its energy. As you make the jigsaw pieces smaller and smaller, the virtual particles can reach higher and higher energies. For jigsaw pieces like Pauli's, about a femtometer across, these energies reach up to a few trillionths of a joule for each of our little boxes. That doesn't seem like much, but remember, the boxes are tiny, so the density is dangerously high. For a coffee cup of empty space, with lots and lots of these tiny little boxes, The total energy stored inside the cup comes out at a whopping 100,000 trillion joules. That's enough energy to boil away all the oceans of the Earth. But why stop there? It's been almost a century since Pauli performed his calculation in the cafe in Hamburg. Since then, physics has moved on. We've developed technology that has enabled us to probe deeper and deeper into the microscopic fabric of the universe. In the tunnels beneath the mountains on the Swiss-French border lies the Large Hadron Collider, CERN's state-of-the-art particle accelerator, a machine that recreates the first moments of the universe, colliding subatomic particles head-on at almost the speed of light. These collisions allow physicists to peer deep into the micro-world with unprecedented resolution, breaking the universe up into pieces that are 10 to the minus 19 meters across. That is 10,000 times smaller than an electron, 10,000 times smaller than the jigsaw pieces Pauli had imagined. When you break down the universe into pieces this small, you can resolve virtual particles popping in and out of existence every billionth of a nanosecond, filling the vacuum with enormous amounts of ambient quantum energy. With this estimate, a coffee cup of empty space would have enough energy to blow up an entire planet. And not just once, more than 100 million times, wiping out every planet in the galaxy. Again, why stop there? The collisions in the tunnel at CERN are at the edge of experimental physics, as it is today. But that is only limited by our technology, and of course, funding. There's no real reason to believe that physics could not go beyond this point. With better machines, we can imagine peering even more deeply into the micro-world, resolving the universe on an even smaller scale. So how far could we go? Well, we could imagine breaking the universe up into pieces as small as the Planck length, which is more than 1,000,000 billion times smaller than the scale of our experiments at CERN. The Planck length is the distance at which the fabric of space and time ceases to make sense, as it becomes overwhelmed by quantum effects. If we tried to break the universe up into pieces smaller than the Planck length, the very notion of space and time would begin to disintegrate. But tiny little boxes of Planckian size are more than enough to worry about. If we break the universe up into pieces this small, we find that our coffee cup of empty space would contain a googol gigajoules of energy. And that is enough to blow up every planet and star in the observable universe again and again and again, more than 1 trillion times. So, should we be worried? Should it terrify us to learn that empty space must contain such gargantuan energies, lurking all around us, between the molecules of air, even in the empty space between the atoms in your body? In a world without gravity, there's nothing to fear. For this Nullpunktsenergie is constant. The energy density of empty space is the same everywhere. That's why we sometimes call it the cosmological constant. To create weapons that destroy planets and galaxies, you need energy differences, gradients in the energy density that allow you to generate force. The true underlying vacuum energy of our entire universe has constant density across all of space. There are no gradients. You couldn't use it to crush a grape, never mind a galaxy. Without gravity, this vacuum energy cannot touch you. But with gravity, that's a very different story. With gravity, the vacuum energy goes one. To understand this, we need to understand how gravity works. Einstein taught us that the gravitational force is very different to the other fundamental forces in nature. In some senses, it's not really a force at all. Gravity is really the shape of space-time, and so it isn't just mass that bends space and time. Mass is just a form of energy. All energy bends the space and time around it, creating the warped shapes in space-time that we perceive as gravity. The Nullpunktsenergie is no exception. The vacuum energy, the cosmological constant, whatever you want to call it, will bend the shape of space and time, even if it is the same everywhere. And of course, the more of this energy you have, the more space-time should be bent. This is why Pauli declared that the universe would not even reach the moon. He calculated the density of the energy in empty space and worked out how much that would bend space-time, quickly seeing that space-time would be bent right back, so that the observable realm could not even reach as far as the moon. But we've already seen how Pauli had underestimated the vacuum energy, guided as he was by the limits of experimental physics in his day. Modern estimates suggest that the universe would contain so much energy in empty space, it would be bent into oblivion, crushed under its own weight. It wouldn't even reach beyond the end of your nose, never mind the moon. And now, we have to state the obvious. The universe does reach beyond the end of your nose. In fact, it reaches 1 billion trillion times farther than the moon. The edge of the observable universe, as we've seen, is around 46.5 billion light-years away. If the cosmological constant is there, it's a whole lot smaller than we expected. In fact, it should be more than a Google time smaller. The energy stored in a coffee cup of empty space cannot be enough to destroy a planet or star. It shouldn't even be enough to crush the smallest insect in the world. This is the cosmological constant problem. Our best and most trusted theories of fundamental physics come together to predict that our universe should be so overwhelmed by the Nullpunktsenergie, by a terrifyingly large cosmological constant, that it simply shouldn't exist. And yet, it does. Why? On the 3rd of September 1949, a filter paper on a weather plane flying from Japan to Alaska detected unusually high levels of radioactivity. The filter paper was sent to the US scientific lab at Los Alamos for further analysis. And on the 23rd of September, US President Harry S. Truman announced that the Soviet Union had successfully detonated an atomic device. The bomb had been detonated a few days prior to the flight of the weather plane at 7 a.m. local time on August the 29th at the Semipalatinsk test site in modern-day Kazakhstan. 10 kilometers south of Ground Zero were 8 men, amongst them Yakov Zeldovich, head of the theory division at the Soviet Nuclear Development Center at Arzamas 16. Zeldovich remembered seeing a bright cone-shaped flash with a tongue of fire coming out of the dust and smoke before stepping down into the safety trench. After 30 seconds, the sound of the explosion reached the trench like a clap of thunder. Some of the men celebrated in praise of Comrade Stalin. Zeldovich stayed silent. To the Soviets, Zeldovich was a silent superstar, a legendary physicist who played a pivotal role in their nuclear weapons program, and one of only 16 people to have been named a hero of socialist labor on 3 separate occasions. Whereas Robert Oppenheimer became less active in physics after his involvement in developing the nuclear bomb, Zeldovich went on to make major contributions to particle physics, astronomy, and cosmology. And it was Zeldovich, 20 years later in 1967 and 1968, who made the world take notice of the cosmological constant problem. It's not clear if Zeldovich knew about Pauli and his enigmatic calculation in the cafe in Hamburg in the mid-1920s, but it didn't matter. Zeldovich was armed with far more powerful tools than Pauli ever had at his disposal. By the late 60s, the general theory of relativity was well established, along with its applications to cosmology. Quantum field theory was fast becoming the dominant description for a subatomic world. It was really Zeldovich who saw that the vacuum ought to be a bubbling broth of virtual particles, endlessly popping in and out of existence, weighing down the vacuum, bending the universe back into oblivion. Zeldovich knew that something had to be wrong with our understanding of the universe, and sensed an opportunity for physics, stating that the clarification of the cosmological constant will be of tremendous fundamental significance for the theory of elementary particles. So what can we do about this cosmological constant problem? Perhaps we should just take an empirical approach. The energy of empty space is whatever we measure it to be. If it's small, it's small. Who cares about Zeldovich and the predictions of quantum field theory? Who cares about Pauli and his idiosyncratic cafe calculations? Perhaps that's just not how nature chose to do things. But this is not very satisfying. The quest is to discover how the universe works, and a wealth of empirical data points towards a micro-world accurately described by quantum field theory, the relativistic version of quantum mechanics developed in the years following the Second World War. We can't just simply abandon it, not after so much experimental success elsewhere. And then there is the general theory of relativity, the zenith of Einstein's genius, describing gravity as the shape of space-time, accurately predicting exotic phenomena like the bending of light around the Sun and the perihelion precession of the planet Mercury, a slow but relentless shift in its elliptical orbit. It too has a huge wealth of data supporting it, even being added to this day. LIGO's detection of gravitational waves in 2015, another feather in its cap. But together, these two great pillars of 20th century physics predict a universe instantly destroyed by the overwhelming weight of the vacuum, by a Herculean cosmological constant, by the Nullpunktsenergie. As Zeldovich realized more than 50 years ago, we are obviously misunderstanding something. Something very important.
Mind-bending.
The cosmological constant problem is such a crisis in our understanding of fundamental physics, its resolution is expected to lead to something profound, a step change in our picture of how the universe really works. Another example of something similar is the famous black hole information paradox, another problem that Zeldovich had a hand in. This is the question of what happens to all the information you throw into a black hole. Does it disappear in violation of the laws of quantum mechanics, or does it survive? If so, where does it go? Just like the solution to the cosmological constant problem, the answers to these questions are expected to reveal something deep about the fundamental fabric of our physical world. And so theoretical physicists are forever looking for the solution to the cosmological constant problem. In the half-century since Zeldovich formulated the problem in modern terms, many solutions have come, but many have also gone. A common thread is assuming that Zeldovich's calculation of the cosmological constant is only part of the story, that the elementary particles contribute an overwhelmingly large vacuum energy, but that there is another piece, another constant from some hitherto hidden sector of the micro-world that cancels out the parts that Zeldovich found. How and why it would be able to cancel them out to such an astonishing level of precision is the key piece of the puzzle. It's like balancing the weight of a trillion suns, accurate to the mass of a single electron. The most popular idea makes use of the multiverse, the idea that our observable universe is just one of many possible universes, each with a different value for the overall cosmological constant, and perhaps other fundamental constants. In most parts of this theoretical multiverse, the scales are off balance, and the overall cosmological constant is large and overwhelming. But in some rare corners of the multiverse, the balancing works, and the overall cosmological constant is small, just like it is in our universe. String theory, our most promising candidate for a theory of everything, predicts that such a multiverse could exist. It has all the right sort of hidden sectors with a multitude of different possibilities. Depending on who you ask, string theory predicts between 10 to the power of 500 and 10 to the power of 272,000 different vacua, different universes with a range of vacuum energies, a spectrum of cosmological constants. This multiverse is known as the string theory landscape, and it's just what we would need to take on the cosmological constant problem with an innovative but controversial idea. But if small cosmological constants are rare in this possible multiverse, how come we find ourselves in a universe with a tiny cosmological constant? This is where some physicists advocate the anthropic principle. The idea is that those universes with a large and overwhelming cosmological constant are uninhabitable because of the enormous weight of empty space. If the cosmological constant is too large and positive, the universe is blasted apart too quickly. So much so that matter is unable to clump together and stars and planets never get the chance to form. If the cosmological constant is too large and negative, the expansion of the universe rapidly gives way to an apocalyptic crunch. The universe squashed out of existence, again before stars and planets ever get to form. It is only in these rare universes, like ours, where the cosmological constant is unexpectedly small, that conditions are just right. A Goldilocks universe with a slow and gentle cosmic evolution, allowing time for stars and planets to form, and providing a home for complex life. Indeed, it is only in these Goldilocks worlds that someone, or something, Howley or Zeldovich, can eventually be born, smart enough to ask difficult questions about the cosmological constant, about the energy of empty space. But not everyone likes this explanation. Some people say that the multiverse and anthropic selection is unscientific, that it cannot be falsified. Although, that is not entirely true. Back in 1997, Nobel laureate Steven Weinberg and his collaborators argued that if the vacuum energy was less than 60% of the total energy budget of the universe, anthropic arguments could not explain why it was so small. This was a testable prediction of the anthropic solution to the cosmological constant problem. And as it happened, less than a year later, astronomers announced the discovery of dark energy, making up around 70% of all the energy in the observable universe. The anthropic principle passed its first test. But people are still searching for alternative ideas that don't rely on anthropic reasoning. These ideas go by many names: supersymmetric large extra dimensions, vacuum energy sequestering, and cosmic relativity, to name but a few. However, there is no consensus, and right now, the mystery of the cosmological constant remains unsolved. And so, we set out to weigh the universe, and stumbled across one of the most embarrassing problems in fundamental physics. We weighed the stars and the planets and clouds of interstellar gas. We weighed the halos of dark matter that shroud our galaxies. And we weighed the vacuum of empty space. We weighed so little. Where was the weight of the bubbling broth of virtual particles frantically popping in and out of existence? It should have crushed the universe within an instant of creation. But it didn't. Our universe is light, a gentle giant that allowed you and I to live on a rocky planet orbiting an ordinary yellow star, somewhere in a galaxy called the Milky Way. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching. We'll see you next time. 100 trillion years from now, the last of a great civilization hides in the darkness. Throughout their glory days, their engineers worked entire star systems. They dismantled planets and asteroids to construct an immense interstellar empire. But now, in the twilight of their time, all of this is long gone. All around them, the universe is dying as the last of the stars are going out. Over countless millennia, the sky has continued to fade into an eternal night, the aging universe gripped by desolation and decay. And so, in the darkness, they wait for the end. Long before they had realized it was coming, they knew that the universe was on a path of inevitable decline. Methodically, they hunted for a final place to wait out eternity, and embarked on their last great feat, of engineering. Around a lost and lonely black hole, they built a new home. With demolished worlds as raw materials, they constructed a shell to completely enclose the darkness. And within this thin shell, barely withstanding the gravitational grip of their savior, they eked out their meager lives. The dwindling light of dying stars rained down upon their final home, whilst their swirling black hole was harvested to power their existence. But more than that, the black hole at their heart gave them the greatest gift of all. For the black hole gave them time. No one remembered the name of the great scientist who had discovered the nature of time. But the astro engineers knew that time was not the same across the cosmos. And here, within the immense gravity of the black hole, time trickled more slowly. Whilst many years passed outside, mere moments flashed by within the immense sphere. And so the last of the civilization watched the future lay out in front of them. But they knew they had only delayed, not averted, their ultimate demise. And the darkness would inevitably envelop them forever. Of course, this story is little more than speculation. But it is built on a scientific idea that changed our universe. It's been more than a century since Einstein's relativity shook up our understanding of time and space. But how does it really work? And what does it really mean? Both time and space seem so commonplace, so obvious, so everyday. But beneath their ubiquity, they hide a multitude of unanswered questions. Questions to which Einstein's theories only begin to answer. What is space made of? Does time exist? And will hunting for their ultimate nature lead to sudden clarity? Or will space and time just become more elusive? Einstein offered them lunch, and they accepted. So he moved a whole bunch of papers from the table, opened 4 cans of beans with a can opener, heated them, stuck a spoon in each, and that was our lunch. Albert Einstein was a busy man, and often missed lunch, and that was back in 1915. In the century since, our lives have only become more chaotic. And that is why a meal kit service like HelloFresh, our sponsors today, are such a great choice. HelloFresh delivers fresh, high-quality produce straight from the farm to your door, with more than 55 weekly meal options. Great for everyone, and especially if you want to stay fit and healthy. I'm a big fan of fitness and eating the right food, but in honesty, sometimes there just aren't enough hours in the day, and a microwavable meal seems like the only option. HelloFresh has saved me from this tasteless horror. The kits are foolproof, genuinely really hard to get wrong, and that is coming from an absolute cooking disaster. And last, but definitely not least, a recent survey found their meals up to 72% cheaper than dining out or grocery shopping. Go to HelloFresh.com and use the code HISTORY16 for up to 16 free meals and 3 surprise gifts. This is a great company, and the cherry on top is that they're also carbon neutral. A big thanks to HelloFresh for supporting educational content on YouTube. As the lonely world lingered on, its beating heart warmed the very fabric of the universe. The civilization had done everything they could to keep going, to put off the inevitable. But try as they might, they could only bend reality. Could not break it. Behind it all is surely an idea so simple, so beautiful, that when we grasp it, in a decade, a century, or a millennium, we would all say to each other, how could it have been otherwise? How could we have been so stupid? What is space? The question seems almost meaningless. As children, we learn to describe our surroundings as up, down, left, right, back and front. We call it three-dimensional and are free to explore each dimension. But just what is it, this universal platform on which we play out our lives? It is a question that occupied the minds of the earliest philosophers. In the 4th century BC, Plato declared that space was the nurse of becoming, a medium in which everything existed but with no qualities of its own, and his student Aristotle agreed that an empty void was impossible. But it would be more than 2,000 years before our concept of space was born. By the coming of the 17th century, modern science was crystallizing. The processes of the universe were being codified into physical laws, and the understanding of these physical laws was evolving from myths and stories to the language of mathematics. Of course, Isaac Newton was at the forefront of this revolution, but before he enters our stage, we must first start with the boat. In 1632, Galileo published his seminal work, Dialogue Concerning the Two Chief World Systems. He was in his mid-60s by this point, and had already had multiple run-ins with the Roman Inquisition for his assertions that the Earth rotated around the Sun. So, he decided to skirt controversy and spend the intervening years quietly cementing his myriad ideas on space and the cosmos into a book. And at one point within this book, he muses on a boat. More specifically, the life of a sailor locked below deck in the windowless cabin, with plates, knives, and a goldfish in a bowl on the table, and a collection of birds, flies, and butterflies. Just what does the sailor experience? Tied up in port, the cabin is a picture of serenity. All is calm as the goldfish swims happily in his bowl. On the table, plates and cutlery remain in their place, and the flying creatures happily flutter about. But finding itself in rough seas, the cabin heaves and falls with the ship. Plates and cutlery are wrenched off the table, water spills from the goldfish bowl. On calm seas with wind-filled sails, the ship would speed up. The sailor would feel this change and see things sliding off the table. But when the wind finally drops, the ship sails smoothly on the glassy sea. Inside the cabin, only calm, serenity, eternity. For the sailor, it would be as if the ship was still in port and was not moving at all. A dropped plate would fall straight to the floor, and the sailor would sit comfortably in a chair. And it was here Galileo realized something. Without a window to reveal the truth, there were no experiments the sailor could do to reveal whether the ship was moving or not. He concluded, therefore, that there must be no absolute concept of being at rest, space. Instead, everyone must experience any smooth, uniform motion in the same way. All uniform motion must feel like simply being still. Galileo declared that any uniform motion is simply relative to any other uniform motion. And with this, the first theory of relativity had been born. Galileo's sailor floats gently on their ship on seas near the Earth's equator, rotating at 1,600 kilometers an hour around the Earth, which in turn orbits the Sun at 67,000 kilometers an hour, which in turn orbits the Milky Way at 720,000 kilometers an hour, which in turn is traveling towards the Andromeda Galaxy at 403,000 kilometers an hour. And yet, he feels nothing on this vast journey, millions of kilometers from his starting point. Unfortunately, upon publishing the book, Galileo once again fell foul of the Church and was found guilty of heresy for his heliocentric view of the cosmos. The work was banned and would not be removed from the Church's Index of Forbidden Books until 1835. But this was not the end. For within a few decades of Galileo's downfall, two of Europe's greatest minds were arguing about the nature of space. One of them, Isaac Newton, was born in England in 1642 within a year of Galileo's death. He, of course, needs little introduction and is known now as one of the greatest thinkers of his age, perhaps one of the greatest of all time. And whilst not forgotten, his opponent, Gottfried Leibniz, is somewhat less well known today. Born in 1646 in what is present-day Germany, he was a leading thinker of his time, writing on mathematics and philosophy. He pondered deep metaphysical questions, including one that still haunts physicists and philosophers to this day. Why there is something rather than nothing. It was in the development of calculus that the two men's feud began. Whilst Leibniz published his work first, Newton claimed that he had stolen his ideas. As president of the Royal Society at the time, Newton set up a committee to investigate the dispute. Unsurprisingly, the committee found in favour of Newton. And so, this animosity carried over to their second disagreement. A simple question. What happens to a spinning bucket of water? Space, Newton declared, was a universal absolute, a rigid stage on which motion was played out, and both space and time would exist in a universe devoid of matter to experience any motion. To argue his point, Newton asked us to think about a bucket of water. If the bucket sits at rest, the surface of the water will be flat and level. But if we spin the bucket, the water spins too and its surface becomes curved. And so Newton asked, just what is the water spinning with respect to? He claimed that the acceleration of the spin was relative to an absolute space, something separate to the object itself. And so spinning a bucket in an empty universe would also curve the surface of the water. But to Leibniz, space in an empty universe, devoid of any matter, simply made no sense. The properties of objects, Leibniz claimed, were essential in defining their meaning. Space only had meaning in the relative locations of objects. And similarly, time only had meaning when discussing their relative motions. Without matter, Leibniz said, space and time simply had no role, and hence, no existence. Sadly, Leibniz died in 1716, with the argument still in full swing, and it was Newton's ideas that stuck. Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. Absolute, true and mathematical time, of itself and from its own nature, goes equally, without relation to anything external. This so-called absolute space and time would be the accepted science for nearly 2 centuries, but with the caveat of Galileo's rejection of absolute rest. Relativity was still part of the argument. But that only applied to space. Time was a totally different matter. With its implicit direction, time appeared completely distinct. For Newton and Galileo, everyone's clock across the universe ticked with absolute synchronicity, a universal beat that ran through every event in the cosmos. 1 second on Earth, the same as a second anywhere else. But is this true? Is time malleable, or an unswerving metronome that drags the cosmos forward? Does time itself have properties, or is it defined only by the events that run in its current? To answer these questions, we must begin not with physicists wondering about clocks, rulers, and motion, but with distant future universe, around the aging black hole, our dying civilization sits. The sitting and waiting is all they can do. With the passing of the stars, more energy has become the most precious thing. To preserve what they had slowly over existence. Every aspect was focused upon survival as their sleepy eyes watched the ever-darkening skies. And as total, universal heat death crept across the cosmos, they realized that time was their ultimate enemy. You may see a cup of tea fall off a table and break into pieces on the floor, but you will never see the cup gather itself back together and jump back on the table. What is time? Like space, the nature of time occupied the minds of many ancient thinkers. In ancient Greece, Aristotle stated that time was simply the steps between before and after, whilst Hindu philosophers saw time as cyclical, from creation to destruction, over 4 billion years. But its true origin remains elusive. Like space, time seems to be something obvious, something that is just present. But it is clearly a different beast. We cannot, for example, freely travel through time. Unlike space, time has a direction, a distinct past, and a coming future. Of course, scientists can be pragmatic and not worry about the nature of time. Coupled with a ruler, a clock completes the experimenter's toolbox. But it doesn't mean we can ignore the question. And so to understand time fully, we first have to think about horses and steam engines. The coming of the Industrial Revolution presented humanity with a problem. The original engines of civilization, draft animals like horses and cattle, were relatively simple things. Understanding how much to feed them, how much to work them, was easy. A certain number of bales of hay could guarantee a day's work from a well-fed animal. But what of newfangled machines, such as a steam engine? How much work can you get out of a heap of coal? This was an important question from an economic standpoint. Do you even bother to replace a horse with an engine if it's going to cost more to feed it? And it was out of this conundrum that thermodynamics was born. Many minds were wrestling over the question of the ultimate efficiency of engines. Indeed, at the time of thermodynamics' inception, a typical engine only worked at 3% efficiency. In a physical steam engine, the heat of the fire is used to boil water. Some of the fire's heat just radiates into the air. Metal scrapes against metal, screeching loud and hot to the touch. Both forms of energy loss. In any physical steam engine, this loss of heat as waste is inevitable. And indeed, within the mathematics of thermodynamics, perfect efficiency is found to be an illusion. The concentrated energy released from burning coal must be degraded as it flows through the engine, and some must be lost into the surroundings. Eventually, a new measure was introduced to account for this increase of decay and disorder, entropy, and it is probability that dictates how this happens. As the early 20th century physicist George Gamow put it, the room in which you sit reading this book is filled uniformly by air, from wall to wall and from floor to ceiling. And it never even occurs to you that the air in the room can unexpectedly collect itself in a far corner, leaving you to suffocate in your chair. However, this horrifying event is not at all physically impossible, but only highly improbable. Gamow goes on to give the waiting time of such an event trillions upon trillions of times longer than the entire age of the universe. Disorder is always, statistically, far more likely. And so, through these new laws of thermodynamics, physicists reveal an inexorable growth in entropy as the universe marches on. A future universe destined to be more disordered and decayed than today's. And this applies not only to steam engines, but whole planets. Stars, galaxies, filaments, all marching from order to disorder. It was in 1862 that the grim logical endpoint of these ideas was proposed by Lord Kelvin, for whom the measurement unit was named. Although mechanical energy is indestructible, there is a universal tendency to its dissipation, which produces exhaustion of potential energy through the material universe. The result would inevitably be a state of universal rest, death, if the universe were finite and left to obey existing laws. And so, was this time? A constantly dying universe heading for inevitable heat death? Stars going out one by one in a steady march from potential energy to waste, leaving the trillion-year-old universe dark and spent. One of the great minds to occupy himself with entropy and the arrow of time was James Clerk Maxwell, the iconic Scottish 19th century scientist. His views on thermodynamics shaped our understanding of heat and gases. He did all of this with the assistance the demon. Maxwell understood the implications of entropy. He knew that if he mixed two gases, one hot and one cold, the result would be warm gas. And he knew that the gas would stay warm and mixed rather than separating into two halves. He wondered, what if we introduced a tiny demon who can sense each and every atom of gas? This demon can turn around atoms, directing slow atoms to one side and fast to the other. As the temperature of a gas is a reflection of the average speed of its atoms, the demon could effectively separate the warm gas into two unequal halves, one hot and one cold. The demon seems to have broken the laws of thermodynamics. It has taken the disordered state, the warm gas, and created a more ordered state, hot and cold gas. And whilst this is only a thought experiment, arguments over the meaning of Maxwell's demon have raged for over 150 years. Some have stated that the demon must be expending energy to sort the gas atoms, and so total entropy will continue to rise. However, some have proposed that it is not energy that is important, but the fact that the demon uses information, namely the speeds of the atoms, to do the sorting. Linking energy, entropy and information might seem a little strange, but over the last 3/4 of a century, this link has become stronger and stronger. And as any touch of a computer will tell you, processing information generates a lot of waste heat. But the situation is even more complex than that. For it is not simply the processing of information that leads to waste heat, but the forgetting. When we add 3 and 2, the answer is of course 5. But if I told you an answer was 5 and asked what two numbers are summed together, you cannot answer. In a similar way, inside a computer, logic gates combine electronic signals to do the addition. Whilst two numbers are fed in, they are forgotten as the single answer is spat out. The calculation is irreversible. The inputs lost to the universe. And in the action of forgetting, the logic gates heat up just a little. In this way, thermodynamics provides us with the ultimate limit, forgetting. Called the Landau limit, it is the inevitable release of energy from erasing a single bit of information. And at room temperature, it is just over 100 of an electron volt. Proven experimentally in 2012, scientists believe that at present, computer chips produce thousands of times more heat than this limit. But by 2035, they will most likely reach it. That tiny bit of waste heat inescapably increasing the entropy of the universe. Ultimately, across the cosmos, it is this irreversibility of calculations that drives entropy to increase. Forgetting information is therefore an essential ingredient to define an arrow of time. Does this mean that for yesterday and tomorrow to have meaning, we must forget? Is the existence of the future implicitly tied to our inability to remember? And it is now we can return to our lonely civilization on the brink of universal heat death in the far distant future, when all useful energy is used up and entropy is at maximum. Would time even have any meaning? So, we have now reached eternity. The foundations of modern time and space can only get us so far. And though they are useful, there is another revolution coming. A new order that will lead directly to the last days of our lonely black hole world. And as we continue in our journey, we are going to have to explore new time and new space. Within their black hole shell, many of the civilization resigned themselves to their fate and dozed their way to the end. But a few curious minds, with their dwindling energy, still wondered about the universe. Great books that had existed for almost an eternity told them how space could bend and curve. Central to these books was the story of light. They knew that light speed was immense and had used it to help measure their empire. They knew that light was a limit they could never break, no matter how hard they tried. And they knew that the speed of light had been the first step in the long journey to understanding how the universe worked. When you are next out of doors on a summer night, turn your head towards the zenith. Almost vertically above you will be shining the brightest star of the northern skies, Vega of the Light, 26 years away at the speed of light, near enough to the point of no return for us short-lived creatures, for no man will ever turn homewards beyond Vega to greet again those he knew and loved on Earth. The speed of light has always been mysterious. Early experiments in flashing lights back and forth had shown that it must be much faster than sound. So scientists wondered, was it infinite in speed? It was in 1676 that Danish astronomer Ole Rømer finally found the answer. Rømer was observing the moons of Jupiter as they circled the giant planet, and timing just when they entered the gas giant's planetary shadow. He had assumed that the orbits ticked like clockwork, and so would be able to predict just when the eclipses of the moons would begin and end. But as he observed the moon higher throughout the year, his predictions got steadily worse, and then better again. It became clear that the accuracy of his predictions depended upon our distance to Jupiter, and he would need to include the extra time taken by light having to travel further. And so, with Rømer's data, fellow astronomer Christian Huygens calculated that light must move at more than 211,000 kilometers every second, not far off our modern estimate of about 300,000. Rømer's observation confirmed that light was fast and finite, but precisely what light was would have to wait for 2 centuries. For as well as the confusing implications of James Clerk Maxwell's demon, he is also famous for intertwining electricity and magnetism into a single idea: electromagnetism. Light, he found, was nothing more than a self-propagating combination of the two, and written into these equations was light's blistering speed. But there was still a problem. Just what was this speed relative to? Maxwell's equations gave no answers, so physicists began to search for a solution. Perhaps, they hypothesized, light traveled in an invisible medium, a mysterious ether permeating the entire cosmos. But that would also imply an ultimate state of rest in the universe, a worrying thought, as this would break Galileo's relativity. The problem was severe. So whilst one group of physicists set out to measure the properties of this supposed ether, others took the evidence in front of them and made an even larger leap. And chief among these was a young Albert Einstein. Einstein wondered why electricity and magnetism would not obey Galileo's relativity. Why should experiments specifically using the flow of electricity or spin of a magnet reveal absolute motion? In a bold step, he declared that they cannot. And with that, a special theory of relativity was born. On Galileo's ship, Einstein proposed all experiments would yield the same results, whether the ship was secured in port or smoothly sailing on a glassy sea. Throwing a ball would of course not reveal whether the ship was moving, but neither would measuring the speed of light. The speed of light in a vacuum was constant. This final statement seemed to fly in the face of the universe as laid out by Newton. In Newtonian mechanics, you could simply add speeds together, and each observer would measure differing speeds dependent on their own motion. But according to Einstein, this was not the case for light. Everyone would measure the same speed, whether the ship was stationary, going at 50 knots, or 50,000. However, if this was true, something else had to give. And the only freedom in the equations was the very nature of space and time themselves. For it to work, each observer must have their own measurement of space, and each observer must have their own measurement of time. With special relativity, it was the speed of light that was absolute, not space and time. space and time were no longer the universal stage on which physics played out. And just as Maxwell had combined electricity and magnetism, space-time, too, was about to unite. Gentlemen, the views of space and time which I wish to lay before you, they are radical. Henceforth, space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union, the two, will preserve an independent reality. In 1908, Hermann Minkowski, Einstein's former professor, came up with an idea. In reaction to the revelations of special relativity in 1905, he had decided to explore the geometry of these new equations. In Einstein's formulation, space was space and time was time, and to transform from one observer's viewpoint to another, you needed to mix the two together. But Minkowski pointed out that it was simpler to mix space and time together into space, and to transform one observer's space-time to another in geometry. And so, finally, combined space-time was born. This new melding of the three dimensions of space and one dimension of time has come to be known as Minkowski space, though Minkowski himself tragically died in 1909, before his idea had been fully embraced by the physics community. Newtonian space and time may have been completely upended, but Einstein was still not happy. Though his ideas had revolutionized our ideas of the universe, they could not account for gravity. Newton's gravitational equations needed the distance between masses, and special relativity now told us that no one could even agree on what these distances were. So Einstein went back to the drawing board and spent a decade thinking about gravity. What eventually emerged from these ruminations in 1915 was a solution that shocked physics to its core. Einstein had taken Minkowski's geometric picture of space-time and made both space and time bendy and stretchy, the presence of mass and energy producing this curvature. Within this general theory, Einstein concluded that gravity, as a force, simply did not exist. The effects of gravity were encoded within the curvature of space and time. Newton's picture of space and time was well and truly dead. For not only were space and time relative, they were flexible as well. The consequences of Einstein's vision of relativity were quickly uncovered. In the special theory, the relative ticks of clocks depended on motion, and whilst everyone feels time passing at 1 second per second, different clocks will tick off different amounts of time. But with the coming of the general theory, time was shaken even more, as where you are also influences the tick of your clock. The presence of mass curves space and curves time, and so gravity can dictate the relative ticking of a clock. The following year, in 1916, Carl Schwarzschild solved the field equations of relativity for a spherical mass, and written inside his equations was a completely collapsed mass, squeezed into a point. Whilst it didn't get its name for another 50 years, Schwarzschild had the mathematics for a black hole. His solution showed that black holes bend both space and time, and with this intense curvature comes intense gravitational pulls, not even light able to escape. In the vicinity of a black hole, where gravitational fields are immense, time becomes more and more curved as you get closer to the center. Compared to clocks in the distant universe, near the heart of darkness, time ticks very slowly. And it wasn't just black holes that sprung from the new equations. In the centuries since Einstein's gravitational insights, many more bizarre solutions have been found. Throughout the relativistic literature, there are wormholes, warp drives, and even entire curved universes, all built from the malleable nature of space and time. In 1919, observations of the deflection of starlight proved his theory and made Einstein a superstar, and so scientists turned their attention to measuring the effects of general relativity to further cement the concept. One of the weirdest of these experiments was undertaken by Joseph Haffel and Richard Keating in 1971. Their equipment was a series of very accurate cesium clocks and a set of jet plane journeys that completely encircled the Earth. To begin the experiment, all the clocks were placed in the same location and synchronized. Some of the clocks then headed off on a plane, some heading to the east and others to the west, some moving with the Earth's rotation, others against it. $7,600 was spent on flights, with 2 seats on each plane going to Mr. Clock. And because they were flying, they were in a different gravitational field to the clocks left behind. After they had circled the world twice, they were all brought together. If the universe was governed by Newton's absolute time, they should all have remained in sync. But if Einstein was correct, relative motions and space-time curvature should have de-synced them. The experiment was run, and the clocks were reunited. They differed by a few hundred nanoseconds. Einstein was declared the winner. But there is one more test of relativity that has proven to be the most spectacular. In developing relativity, Einstein found stretchy space-time can also wobble and ring. Just as Maxwell found that electricity and magnetism could ripple, so could gravity. But Einstein couldn't decide if his mathematics were correct or if he was fooling himself, and struggled to conclude whether these gravitational waves were a part of reality. In 1974, Russell Hulse was a young astronomy student who made a spectacular discovery. With his supervisor, Joseph Taylor, whilst peering into the universe with a 300-meter Arecibo telescope, he found a pulsar, the rapidly spinning dead heart of a star. This pulsar, PSR B1913 plus 16, was spinning 17 times a second and was not on its own, but orbited another dead star heart, a neutron star. And with the regular beats of the pulsar, they were able to accurately chart the cosmic dance. What they found, however, was quite unexpected. With Newtonian gravity, these dead stars should orbit each other for eternity. But Taylor and Hulse found that the orbits were shrinking, and the stars were slowly but steadily being drawn together. Somehow, the energy of their orbits was leaking out into the universe. And it was then Taylor and Hulse realized Einstein's gravitational waves were an ideal culprit. They delved into the mathematics of general relativity and calculated how the orbiting stars formed ripples in spacetime, showing how they could carry away precisely enough energy to explain the orbital demise. In 1993, Taylor and Hulse received the Nobel Prize for their discovery, and 24 years later, the prize was awarded for the direct detection of gravitational waves. That experiment was the Laser Interferometer Gravitational Wave Observatory, or simply LIGO for short, which, with unimagined sensitivity, can feel the tiny ripples of space-time. LIGO has opened a new and exciting window in the universe. They are uncovering emerging black holes and the collisions between neutron stars. And now, astronomers even plan to hunt for the oldest gravitational waves, formed in the birth of the universe. And so, in this new world ushered in by Einstein, it is clear that the entire cosmos is written in the language of gravity, curve and warped, space and time. But there was one more secret, one cover, hidden in the equations. First realized by Alexander Friedman in 1922 and later proved by Edwin Hubble, the expansion of the universe is the expansion of space, expanding from a single point 13.8 billion years ago, known today as the Big Bang. Put very simply, there was less space yesterday, and there will be more space tomorrow. Every galaxy has been found to be moving further and further away from us, bar our local group, at an average rate of 70 kilometers a second per megaparsec, which actually means that at the moment, for every 3.26 million light-years distance away from us a galaxy is, it is moving away from us at an extra 70 kilometers a second. So a galaxy 326 million light-years from us is moving at 7,000 kilometers a second, and a galaxy 32.6 billion light-years away proceeds from us faster than the speed of light. This may seem bizarre, After everything we have learned up until this point, that the universe's speed limit only applies to objects moving through space. And these galaxies are not moving through space away from us. Space is simply growing between us. This expanding universe makes curving and bending space-time even more complicated to understand. As equations show that space is infinite, what is actually happening is that the universe is becoming less dense. And clearly, this decrease in density is not completely uniform across the cosmos. You, for example, are not slowly drifting apart. Individual galaxies too hold themselves together due to their mutual gravity. But as this gravity is a manifestation of the curvature of space, what happens at the boundary between expanding and non-expanding space? That is not the only problem, as expanding space makes the form of yesterday's space-time different to tomorrow's space-time, thus breaking what was thought to be one of the key properties of the universe: conservation of energy. The importance of symmetry in physics was laid out in detail by mathematician Emmy Noether. In this case, a symmetry meaning that when you change your situation, the physics remains the same. Changing location doesn't change physics, meaning momentum is conserved. And the fact that physics is the same today and tomorrow gives energy conservation. But in an expanding universe, where space-time is changing, this symmetry is shattered. As space grows, it doesn't stretch. It doesn't dilute. There is just more of it. But as photons travel across an expanding universe, they are stretched and they lose energy. And galaxies are robbed of their speed as their motion grinds to a halt. This way, energy is simply not conserved as the cosmos grows. A conundrum that causes problems for physicists to this day. And so, it may now seem that space has finally become physical, real. After all, it can bend, expand, curve, and ripple. But there is a final twist, one final rug to be pulled out from beneath us. And this can be summed up in the words of the Nobel Prize winner, Steven Weinberg. How is it possible for space, which is utterly empty, to expand? How can nothing expand? The answer is space does not expand. Cosmologists sometimes talk about expanding space, but they should know better. To the novice, this statement must seem almost bizarre. How can a leading scientist make such a claim? Well, because he is absolutely correct. In Einstein's relativity, space-time is truly nothing. The mathematics look like bending and curving, but in reality, relativity tells us space is nothing and has no properties. But what of time in this new picture? Just how were seconds, minutes, and hours affected by the dawn of relativity? To the future civilization, time meant many things. They knew that their time was unique, unshared by any others. They understood that clocks ticked differently depending on where you were and what you were doing. Their engineers had used this malleable nature of space-time in shaping their civilization. Great portals of distorted time and space permitted travel across the empire, whilst the slow ticks near the gravitational pull of a black hole had been used to stretch time and allow them to watch the end of everything. People like us that believe in physics know that the distinction between past, present, and future is only a stubbornly persistent illusion. With the coming of Einstein's general relativity, physicists were presented with a new headache. They knew that every particle in the universe had a past, present, and future, and like a line drawn on a map, they could chart the journey of a particle through the 4 dimensions of space and time, tracing out its individual world line, from the past to the future, through a series of nows. Each particle in your body, each electron and quark, journeys on its own world line, before you were conceived, the world lines were dispersed. But as you grew, many world lines condensed into a bundle, which is you. And when you are gone, these world lines will again scatter. For a fleeting moment in the life of the universe, you exist as little more than a collection of world lines, a brief knot in the fabric of eternity. Whilst unsettling, this appears to make sense. So where's the headache? Firstly, we have to remember what the relativity of time really means. With no absolute time, there is no uniform cosmic clock. And this means that there is no such thing as a unique present, a true instant of now. Without an absolute definition of a cosmic now, just how do we define a unique notion of the past? Just where does the future begin? And so, headache. Within the equations of relativity, all pasts, presents, and futures are already written. The entire history of all things is already out there, somewhere. This notion, known as the block universe, has bothered many physicists and philosophers, as without a now, the cosmos simply cannot unfold from moment to moment. All we can do as we trace out our world line is follow our predefined path, and concepts dear to us, such as free will, are lost. But this cannot be correct. We clearly remember the past, and the future is a mysterious door that is yet to be opened. They are clearly different. Or are they? Consider two electrons hurtling towards each other. Both carry an identical negative charge, and through electromagnetism, they repel. As they get closer, the repulsion grows and their motion gradually slows, stops, and reverses. Eventually, the electrons hurtle away from each other back the way they came. There seems nothing strange about this. But imagine we filmed the interaction between the two electrons, and then showed the film to an audience of physicists, playing a mirrored version, the left switched to right, and vice versa. Your audience of physicists would notice nothing amiss with the movie on the screen. Switching left and right does not alter the physics. But what if you went one step further? What if you were very clumsy, and instead of switching left and right, you switched past? Future. Film now runs backwards. Time has been reversed. Your audience stares at the screen. What do they see? In this time-reversed movie, two electrons hurtle towards each other. They get closer and closer with their repulsion growing. Eventually, they halt in their motion and start to move away again. And with nothing out of the ordinary, the audience nods in approval at this simple display of physics. But how is this possible? If you had run the slapstick of Laurel and Hardy backwards, the viewers would have noticed, and would immediately know that something was wrong with the arrow of time. And herein lies the question: why is the electromagnetic interaction between electrons insensitive to the direction of time? And not just electromagnetism, but gravity and the strong nuclear force are also unaffected. The weak nuclear force does misbehave slightly, but it is a very tiny effect. It seems that at their core, the universe's microscopic fundamental interactions do not possess an arrow of time. Time could flow one way or the other, and they simply didn't care. This leaves us with a disconnect. The macroscopic, large-scale world we inhabit certainly does know about time. Cooling coffee, burning wood, exploding supernovae, these are not processes that can simply be run backwards. You cannot unscramble an egg. But with a little thought, this seems strange. Clearly, our large-scale world is nothing more than the collective properties of an uncountable number of atoms. And these atoms are interacting through a fundamental force, electromagnetism, each of the myriad of electromagnetic interactions unaffected by the direction of time. So how can such an arrow emerge from the multitude of time-ignorant interactions that take place every second? How does time emerge? In the simple view of the block universe, it stretches infinitely far into the past and infinitely far into the future. But this block universe clearly doesn't appear to resemble our own. For we know that our universe didn't stretch infinitely into the past, it had a beginning. From observations, we know that the universe was born almost 14 billion years ago. We don't know the process that brought it into being, but it was born with both space and time. Just where and how space and time came to be in the universe remains a mystery, but they have remained an integral part of the cosmos since its inception. And there are other mysteries about the birth of the universe that we don't understand. In particular, it appeared to be extremely special, being both hot and dense, and strangely smooth. And this smoothness meant that the newborn universe had a very particular property. The universe was born with very low entropy. It might seem strange that smoothness implies low entropy, as a gas spread throughout a room has higher entropy than gas all squeezed in one corner. But for matter in the universe, this smoothness meant gravity could do its work and fall together, eventually crumbling at the starting galaxies. And so, as the universe expands, its entropy increases as the matter evolves. Gravitational potential energy is steadily converted into stars, planets, and people. Eventually, this energy is processed into waste heat that spreads throughout the universe. And it is this change from low to higher entropy that imprints onto the cosmos its arrow of time. Recent Nobel Prize winner Sir Roger Penrose has thought hard about our universe's initial entropy. He has concluded that the probability of this occurring by chance is 1 part in 10 to the 10 to the 123. Clearly, there must have been something special about our universe's birth. But what this was, we still don't know. And so, would this mean that the blocked universe has no innate arrow of time? Without the Big Bang, would it be impossible to distinguish the past from the future? Imagining how we would experience such a universe is very difficult to do. But indeed, maybe our ability to imagine anything at all is ultimately because of the special birth of the universe. On the 10th of June 1944, a British Halifax bomber was flying over France. With 400 other bombers, it was supporting the D-Day landings at Normandy. But near the city of Laval, the aircraft was struck by German flak and crashed in flames into the French countryside. The entire crew perished in the crash. 7 lives were lost. 7 lives in a war that eventually claimed millions. The pilot was a 33-year-old Dutch volunteer, Willem Jacob van Stockum. And whilst his name is not familiar today, Van Stockum was the man who discovered time travel. Of course, by the 1940s, time travel was a staple of science fiction. The Time Machine by H.G. Wells had been published half a century earlier. But this was all fantasy and whimsy and a firm impossibility in Newtonian space and time. Yet within the new world of relativity, Van Stockum had discovered a scientific basis. Mathematically, relativity is notoriously challenging. Einstein himself had wondered if his field equations would yield any analytic solutions. But merely a year after presenting them to the world, the first such solution was found. A Schwarzschild derived his black holes. And so, by the 1920s, the hunt was on for the mathematical form of the entire universe. Along with the giants of relativity, Einstein, Friedman, de Sitter and others, laying down rules, finding expanding space which itself could be curved, and even space where parallel lines could converge and diverge, some scientists explored the mathematics of hypothetical universes. And Hungarian mathematician Cornelius Lanthos had found a